Hey, this is Horner. We're going to look at the first part of Chapter 3. This is my version of what you see in your book. Kinematics. Kinematics is really just that branch of mechanics that studies the motion of a body, and it really doesn't care what caused the motion. So mechanics, we said, was force and motion. Kinematics is just the motion itself. So we need to define a few things. A particle is something that just has position, so you can find it somewhere, and it has mass. It does not have any size or volume, but it is located at one point in space. So let's just think about position. Position is just the location of a particle in space. It's in one dimension. Could be in 2 dimensions or even in 3 dimensions. And so you'll see we'll use either x-axis, x and y, or x, y, and z. Here is a particle, and it's just at the +1 position. And so we're going to say that its position x is equal to 1 meter. That x does not mean distance, okay? So this is not distance. Distance, we really need to have 2 reference points, so be really careful. That is its position. It is at x is equal to 1. Distance is different. Distance is a total length path, or the total length of the path traveled by an object, and it does not depend on direction. For example, we could say, how far have you walked? So here is what we're going to do. We're going to say we're starting at x original, or x initial, which is the I, is equal to 1 meter. And we're going to travel to the final place, which is x is equal to -1 meter. Our distance here is 2 meters. So we ignore the negative. We're just going to say we went 1, 2 full meters here. So that is our distance that we moved. Displacement is a little bit different. So this is the change in position of an object. It only depends on the initial and final positions and not really ever on the path. And this does include direction. So because it includes direction, it is a vector. So this is a vector quantity. How far are you from home is essentially what you can think of. It is represented by delta x. So remember, x is position, so this would be change in position. And so here our change in position is x2 minus x1, where our final position is x2, and our original position is x1. The distance that we moved by this particle, remember, was 2 meters. And so if I think about the displacement is -2 meters. Why is it -2 meters? Well, remember we said delta x is equal to x2 minus x1. So this is my final position. My final position was -1 minus my original position. And I end up with an answer here of -2 meters. So this gives it direction, and that's what makes it different from distance. Once again, distance here is a scalar. So there's no direction here, and displacement is a vector. And so we see that it does have a -2 for its value. Next thing here is a little bit more on distance versus displacement. This is a nice picture to kind of show you what happens. If I start at A, and let's say I go around this curve and I go to B, we'll represent that as 100 meters. The other thing that we could do is we could think about the displacement. And the displacement, remember, is just looking at starting at A and moving to B, and just the distance between the two. So that is called displacement. So just from point A to point B, we don't worry about the path that we took here. We're just straight. Sometimes they call this as the crow flies, or just the straight line path is essentially what you'll see. For this next part, we're looking at average speed. So they're going to use S for average speed here. Sometimes they'll use V, and it will either have an AVG down here like this, or they will just put a V, and you'll notice that it's not bold and doesn't have any line on the top. So speed is not a vector here. It is actually a scalar. It does not have any direction. So they'll say your average speed is just equal to distance divided by time. And you can kind of see what they're doing with all those abbreviations in the bottom. Average velocity is a lot different. Average velocity, sometimes they'll put a little mark over the top to indicate that it is velocity, which is a vector, and that is that change in position over change in time, or the displacement over time. Remember, speed is the distance over time, not the displacement, just the distance itself. And remember, displacement is final minus original position, and it can be negative. So just some definitions that you probably need to kind of think about. Average speed versus average velocity. Same thing here. We see this butterfly actually flies along the path, and so that would be the path followed. That would be the distance. And we would do average speed based on that distance. But if I wanted average velocity, I would just start at A and go a straight line path all the way over to E. So here our average velocity would be 0.5 meters per second, and our average speed would actually be less than that. Just a little bit more about average speed. Average speed is always positive. Average velocity can either be positive or negative. So just a review. The absolute value of velocity can be used for speed if the object does not change direction. If it just changed direction, then that tends to be a problem. Instantaneous velocity is the velocity at a very short period of time. So if you're driving in your car and you look down at the speedometer and you see that you're going 55 miles an hour, then that is a instantaneous velocity. Instantaneous velocity on a graph is kind of interesting. So here I've got a position versus time graph. And if I want to know what the instantaneous velocity is at any point, I will just go through and I will draw a straight line that is what we call tangent to the curve. So that's where it meets just at one point. And you could draw a perpendicular line right through this. So that perpendicular line would basically be right here. So that makes that 90-degree angle with wherever we're at. So this is instantaneous velocity. We're just looking at the slope of that line, of that tangent line to the curve. If we look at this next one, instantaneous velocity, your book defines it as the limit as t approaches 0. So you're looking at it for a very short amount of time of the change in the position. So they're going to use r here. For a change of position, so just another way of doing notation, all over the change in time. And so once again, here we go, we're looking at change in r over change in time. They're making it smaller and smaller until we get to a point where we just are tangent there. So they're showing a little bit more detail where that tangent line came from. We've done a little bit with motion diagrams already. This just shows the position of an object at equally spaced times, and so we know that this object is speeding up as it goes, and so we can see that in our motion diagram. For velocity, this is just a graphical representation between position and time. If I do the slope of the chord, that gives me average velocity over a period of time. So I'm looking at the velocity from, looking at the position change from time 1 all the way over to time 3. And if I take those 2 points and I find the average along that line, then that would be my average velocity. If I then kind of move that until I have a tangent line, remember that is instantaneous velocity. So the slope of the chord gives average velocity, and the slope of the tangent line then will give instantaneous velocity. So this one is instantaneous velocity, this one is that average velocity. And those are the two things that you see. For the next slide, this goes a little bit more into average velocity again. This is position versus time. And if I go from A to B, we know here is my change in position all over my change in time. So we can think about those two components of that line, or just the two spots. So that's our average velocity for those two lines. Average velocity, if I have something like this, remember we've got to do the tangent line. So if I want to know the secant line, if I do this, A to B, I can find my average velocity for that line. So that one is a little bit different. It's still determined by using the slope, but notice that this is curving a lot, which means that we're accelerating and decelerating as we go through. For example 3.4, they want us to use the figure to estimate the velocity of a train in kilometers per hour at 40 minutes. So we're doing it right here at this point. So to find out what the velocity is at that 40 minutes, we need to do a tangent line and find the slope of that tangent line. So at this point, we can look at a tangent line that we've drawn, and we've got some points here. we've got 30 minutes and we have 57 minutes. We also have negative 25 kilometers, and here we've got 15 kilometers. So what we'll do is let's go ahead and find that change in position. So that would be my final position, which is negative 25 kilometers, minus that positive 15 kilometers. And when we do that, we're going to end up with negative 40 kilometers, and that is going to be our displacement. If we do the same thing with the time, we're going to take 57 minutes minus 30 minutes, so this is our change in time, and we end up with 27 minutes, which is about 0.45 hours. Now we can find out what that instantaneous velocity is. So it'd be negative 40 kilometers all over 0.45 hours. And we end up with approximately somewhere around negative 89 kilometers per hour. And so that's what that instantaneous speed would be at that, or instantaneous velocity would be right at that point. For the next part, this is finding displacement with constant velocity. So if you're traveling with a constant velocity, I can find what my distance that I've traveled, or my displacement, by just looking at the area under this curve. And so we've done this in class before. We did it very briefly, but all this helps us see is that if I know my velocity is equal to my change in position over change in time, that means that my change in position, my change in position is equal to my velocity times that change in time. And velocity times change in time here will give me the area of this under the curve. And so that's a pretty useful thing to be able to use. Same thing here, I can look at the area under the curve even if I have a curve. So here I could go through and make very small little times, and I can add all those up, and I would find this area. To do this precisely, we would need to use calculus, but we're not doing calculus-based physics, so we won't do that. If I do want to do this, I'm going to have to think about just kind of counting some boxes underneath. So up at the top, if I want to find the displacement in this little area here without using calculus, I could say that there's approximately 12 boxes here, and we could multiply that times 0.6 kilometers, and that would give me 0.72 kilometers. Here, each box represents an area of displacement of about 2 meters per second times 300 seconds, and so that's about 600 meters or 0.6 kilometers. So each one of those boxes is about that. Same thing for this one. We've got somewhere around 60 boxes. Notice that it is in the negative direction, negative velocity here. And so we're going to take that, sorry, there's just negative 60 because it's below the line, times that 0.6, and we end up with negative 36 kilometers. Acceleration is a change in velocity, and so that's the term we use. We can be speeding up, we can slow down, and we can also turn. So when you make a turn on a curve, your speed stays the same. So your speed can be constant. You can also speed up and slow down. Your speed is constant, but notice that when we are driving along this curve, at each point here, my velocity changes. Why does it change? Because I am changing direction. So anytime I change direction, regardless of whether or not my speed changes, that is also an acceleration. If you don't believe me, go get in your car, drive down the road, and then take a pretty sharp curve. You'll feel yourself accelerating, trying to pull yourself in. And that is just a pretty basic definition of acceleration. So for accelerated motion in Physics 150, we generally assume that acceleration is constant. We won't do any change in acceleration at all. With that assumption, we're able to use the equation acceleration is equal to the change in velocity all over the change in time. The units for acceleration that we'll use are meters per second squared. And if we're dealing with force, we could also say that that would be a Newton per kilogram, and you'll see why. We've kind of done that a little bit already, but we'll go through it again. The sign of acceleration can be positive or negative, depending on whether you are moving with or away or against the direction of motion. And the general rule here is if the sign of velocity and the sign of acceleration are the same, you will speed up. So for example, if I have a velocity equal to 30 meters per second and I have an acceleration equal to 5 meters per second squared, then I will speed up. If the sign of the velocity and the sign of acceleration are different, then the object slows down. And there's two examples I can do here. Let's do the one we were doing before. Velocity is 30 meters per second. That's what I start at. And I have an acceleration now equal to negative 5 meters per second squared. So that means I'm slowing down. If my velocity, let's say I'm going in the opposite direction, so I'm going negative 30 meters per second, and my acceleration is now positive 5 meters per second squared, we still consider that a deceleration or a slowing down because the signs are in the opposite direction. For the next slide, this is just your book's definition of acceleration, and we're going to look at Newton's second law of motion as we do this too. So here we're saying that the change in velocity over the change in time is equal to the sum of all the forces acting on you divided by your mass. And here our change in velocity, we've already said, is just final minus original velocity, and the change in time is final minus original. So this will be pretty critical and pretty important for you to know. Let's just go back and one more time review. Remember, if our original and final velocities are going in the same direction, I'm speeding up. If my original velocity and my final velocity are going the same direction, but my final is less than my original, then I am decreasing speed. This talks a little bit about that turning. So as I turn, my change in velocity can happen even if my speeds are both the same along that curve. Going back to acceleration, the rate of change of velocity, that quantity delta v over delta t, is acceleration. And then these are our equations that we're going to use. And this equation can be written a little bit better. We can actually say that the acceleration is equal to the sum of all the forces acting on something divided by the mass of all those objects. This becomes the famous equation F is equal to ma. We can do this in both the x and the y direction, and we can find the acceleration in both the x and the y direction for something that's accelerating in both of those directions. So that is our unit, meter per second squared. We also said that the acceleration unit can be a Newton per kilogram, and that's because if we go back to this equation, you'll notice that force is measured in newtons and mass is measured in kilograms. So something pretty easy to see as you go through. Average and instantaneous acceleration, we also have those along with what we had with the velocity. So more generally, Newton's second law is a relationship between the net force acting at any instant and the instantaneous acceleration at that same instant. So we're going to use instantaneous acceleration more often than we do anything else. Your average acceleration during a period of time or a time interval is just that change of velocity over change in time is kind of what we were saying. And we can also do those in the x and y direction too. Instantaneous acceleration, your book defines as we're approaching a very, very small amount of time, so we're getting closer and closer to zero, and we're looking at the change of velocity at that very small amount of time. So here we go, we're looking here at the velocity in the x direction and the time, and we notice that as time goes on, we have a big acceleration because we have a very large slope. And then as we start to slow down, our acceleration is getting smaller and smaller. So as our velocity gets closer and closer here to zero, we see that our acceleration, which is the tangent line, continues to become flatter and flatter, or we get a smaller and smaller acceleration variable. This is a good example. We have a sports car starting at rest, can achieve 30 meters per second in 4.7 seconds. There's a figure that we're going to use next, and they want us to find the following things for that car. So they want us first to find the average acceleration from 0 to 30 seconds. So this is our figure that we're going to use. We'll notice that we have a velocity that is changing, so it's becoming less and less over time. So our velocity is increasing, but the slope of the line that we would get with this would be decreasing as we go. So we're going to have to look at some instantaneous accelerations. For the very first one, they wanted us to find out when we get up to 30 meters per second what that average acceleration is. So we're going to take our final velocity minus original velocity, and we're going to divide by that change in time, and we see that from 0 to 30 we have an average acceleration of about 6.1 meters per second squared. For letter B, they wanted the instantaneous acceleration, and so if we're looking at that 55. So here is a tangent line right at 0. So we're going to say our furthest out y value here for velocity is 55. Our original is 0, and it's taking 6 seconds to get up to that. And so we're going to divide the two, and we find out that we started with an acceleration of 9.2 meters per second squared. To find the change of position, that is just the area under the velocity versus time graph that is shaded. So there's about 75 boxes there. So the displacement is 75 times 10 meters, and that would give us that 750 meters for that change in position. Finally, the last thing they want us to do is find the average speed. So we just have the change of position, which is 750, divided by our change in time, which is that 19.1. So we're looking at the whole thing here, and that gives me 39 meters per second. We're going to stop there, and we will go through Newton's second law in the next video.